Welcome to Study Loop.
So here we have a gas with a specific number of moles in a cylinder, and we have a chemist that heats the gas first by adding the given quantity of heat, this. And so this is the first process, thermodynamic process, and the second thermodynamic process is when he allows the gas to expand, and the gas gains twice of its initial volume. So for the part A, we need to solve for the temperature that comes after the first part of the process, or the heating part. In order to do so, we know that the Q equals, and in this case, constant volume, heat capacity, and the change in temperature, which is equal to N CV TB minus TA. From here, we can derive the formula only for the TB by moving this part to the left-hand side and then adding this part, this term, to both sides. So this way we derive that TB equals Q over NCV plus TA. Since we know the values here, we can say that this equals to 1.52 times 10 to the fourth. This is joules over 2.5 moles times 20.76 joules per mole Kelvin, and this is all going to be in kelvins at the end, plus 293 kelvins, which therefore equals TB equals 585 kelvins. Also, in relationship to volume, we can say that after the heating process, for the expansion process, which is happening at the constant pressure, we know that the ratio formula will be true. So the ratio formula is that Tc over Tb. Since we have from the point A to the point B, this is the heating part, when the chemist heats the gas. From the point B to the point C, this is the expansion part, when the gas is left out to expand freely. So here we are doing for the B to C part of the process, and this is equal to Vc over Vb. And from here we can derive that Tc equals, and here we have 2 Vb, since Vc is twice of the Vb volume over Vb, this will cancel out, times Tb. When we substitute the known values, we obtain that this is equal to 2 times 585 kelvins, and therefore Tc equals to 1170 kelvins. Therefore, we have finished the part A of the problem. Now, for the part B of the problem, we are asked to find the total work done for both processes. So we know immediately that the work done will be the addition between work from A to B plus work from B to C. Observe that since the volume is constant for the process from A to B, this part of the work will be equal to 0, and therefore we only need to calculate for the VB, for the work WBC part, and we can express the work done here from the formula work from B to C equals P times delta V. But from the ideal gas equation, we know that P times delta V equals N times R times delta T. So this equals N times R times delta T. and this is also equal to n times r, and then we subtract Tc minus Tb, since it is from B to C change. We can now directly substitute values and find that it is 2.5 moles times 8.314 joules per mole Kelvin times the difference between the temperatures. And by doing this, we obtain that the value for the BC work is 11.5 times 10 to the third joules, or just 11.5 kilojoules. Actually, this would be 12 to the 12.5 to 10 to the third. So the final result is that W equals WBC, which equals 12.15 kilojoules. This is also going to be 12.15 here. So this is the answer for the part B. And for the part C, we need to find the internal energy change. We need to find how much heat is added, and for the part D, we need to find the internal energy change. So the addition of heat in this case, but for the part of the process where the gas expands, so it is from B to C, since we know how much heat is added in the first part of the process from A to B. So for the part C, we can state that Q equals, and now the pressure is constant, so Cp delta T BC. And in this case, this is equal to 2.5 moles times 29.07 joules per mole Kelvin. This is corresponding to the given gas, and the difference in the temperature, so it will be from the known values, kelvins. And finally, when we put these values into a calculator and evaluate them, we obtain that Q equals 42.5 kilojoules. For the part D, we need to find the total change in internal energy. So we know that the total change in internal energy, similar to the work done, is the addition of the total change in internal energy from A to B, and plus the change from B to C, change of U from B to C. In the process AB, since the volume is constant, the work done is zero, we can say from the first law of thermodynamics that Q AB equals delta U AB plus work, which is zero. So this can be directly substituted since we know the QAB value. Now for the part BC, part of the process, we will need a different kind of evaluation, but also we should actually calculate delta UAB using standard formula where the process is happening under constant volume. So it will be from this. we can use this formula. N times Cv times delta T from A to B. And this is equal to 2.5 moles times 20.76 joules per mole Kelvin times the difference in the temperatures. So minus 29.3 kelvins. And when we put these values into a calculator, we obtain that delta UAB actually equals to 15.15 kilojoules. For the part between B and C, also from the first law of thermodynamics, we can say that UBC equals QBC minus work done between BC. Here we should substitute the corresponding formulas that goes as follows. And Cp, since the pressure is constant, the change in temperature, Bc minus Nr and delta T, Bc. So we can write this down as N times delta T Bc, this is the common parts for the terms, and then we will have Cp minus R. We can substitute the known value. This is the subtraction between Tc and Tb, so we can immediately say that delta UBC equals, and now for all of the known values we have 2.5 moles, and in the brackets the difference between the temperatures, and in these brackets the constants. This will all be in joules, but we will express this in kilojoules because it is more convenient. This is equal to 30.3 kilojoules. Therefore, finally, delta U equals to 15.15 kilojoules plus 30.3 kilojoules. And the final value is delta U equals 45.45 kilojoules. This ends the last part of this problem, and we have evaluated everything that the problem asked us to evaluate. I hope you find this helpful, and I hope to see you in another lesson.